let us now talk about motion. In physics, we measure things, and by finding out the value of those quantities, we find out other things. So we need to understand how it is that we quantify motion, how we measure it. Well, to start with, take a look here. We have a small car on a track, and we're going to allow it to move down the track shortly. But I want you to see, first of all, that we have a meter stick down on the bottom, because what we're going to do is we're going to measure the position of the car at this point here, and then we're going to measure the position of a car after it has moved along. What we're interested in, to start with, is the difference in its position. That we call the distance. So here we go. To start with, it is at 20 centimetres. Turn the car on. It is now at 90 centimetres. Of course, this is a difference of 70 centimetres, or a distance of 70 centimetres. When we're talking about motion, it makes sense, if things are moving at this sort of scale, to eventually describe things in meters per second. You may have heard other units for speed, like kilometers per hour, things like that. But in the classroom, we would say meters per second. And so here, it has moved through 70 centimeters. We should convert that first into meters. So it would be 0.7 meters of distance moved. The next thing we should measure is the time. So what I need to do is get a stopwatch and find out how long it takes to move through that distance. So now I have a stopwatch, and I'm interested in taking two measurements this time. First of all, I need to record the change in its position. That, the difference, is going to give me the distance that it has moved. I also need to measure how long it was moving for. And let's do it right now. So we'll start it off at 20 centimetres once more, and we'll start it in 3, 2, 1. It took 5 seconds, or 5.87 seconds, to go through the 70 centimetres as before. We can use these two pieces of data, the distance travelled and the time taken, to calculate the speed. So, on my calculator, 0.7, the distance, divided by 5.87, the time, gives us a speed of 0.11, or 0.12 meters per second. So every single second, this car moves about 12 centimeters. And so with that information, we could then guess how long it would take to do the entire length of this track. So how long is this track? Well, this track starts at 20 and it goes all the way over here to 200, that's 180 centimeters, and it does 12 centimeters every second. So that means I think it should take 15 seconds to do the full length of this track. Let's see. Okay, 3, 2, 1. Here we go, folks. This is really important. How's that, eh? Love it when the plan comes together. So let's formalise this. We spoke about how there were two different positions. Position 1 and position 2. Now, if I found out what the difference was between them. So I basically subtracted my starting position from my final position. I would end up with a new quantity, and that quantity is distance. Distance. And distance is measured in meters, always. The other thing that I would be interested in is my time interval. So I would technically have 2 times the time that my car finishes and subtract away the time that I started with. Now this causes some confusion because I started at time equals 0, but that doesn't mean that I started my car moving at the beginning of the universe. No, I just started it at some arbitrary time and then let it run for a few seconds and then stopped it. Now of course the stopwatch starts at 0 and it ignores whatever's happened before, it doesn't care. And it measures not necessarily when in the day this happened, but just how long it took for something to do something. It automatically measures the time interval, and so we don't need to do this calculation. And that time interval we just simplify and call time. And so time is the second thing that we must measure. Now, when we're talking about physics experiments, we must talk about the quantities that are being measured. We must also talk about the devices, the apparatus that enable us to quantify these quantities. So, for example, a meter stick is what we measured the first one with, and a stopwatch is what we measured the second one with. Now, the relationship that we're working out here introduces to us a new quantity that is speed. And speed we can work out by working out how many meters it has covered in a time interval. And so speed is simply how far you've gone divided by how long it took you to do it. And you can see that if this is measured in meters and this is measured in seconds, then speed is going to be measured in meters per second, sometimes written like that. And that's it. Speed is a way of quantifying the rate at which you're moving. If your speed is higher, you're moving faster. Now this device here is another way of measuring distance. It is in fact a trundle wheel. What happens is you put it on the ground and the circumference of this wheel is exactly 1 meter. And so what I can do is if it's a larger distance than what I could comfortably measure with a meter stick, I would use one of these. Now I'm going to do a little experiment for you here. I've got the trundle wheel and I've got a stopwatch, and what I'm standing on is a hoverboard. And I'm going to move down this corridor, but I want you to notice something really interesting. It's about my speed. I'm going to vary my speed. At times I'm going to go as fast as I can, and at times I'm going to go much slower. And hopefully at the end, with these 2 pieces of equipment, I'll be able to take a measurement of my average speed. So I shall go over here. And off we go. Slower, faster, and stop. So, what I've now got here are 2 measurements. The first is what it says on the trundle wheel, which is that I covered a total distance of, well, it's on the boundary, it is, I think, 11 meters and 95 centimeters, 11.95, we'll call it 12, and I did it in 8 seconds. Now what that means I can do is I can take the total distance that I have moved and divide it by the total time it took me, and it would give me an average speed. At times I will have been moving faster than this speed, and at times I would have been moving slower. But on average over the whole journey, it would have simply been 12 divided by 8.37. Now, so long as I travel in a straight line, so long as I have something that would measure the distance and the time, I can always work out the speed. So let's give it a go. Travelling a straight line this way, that is a grand total of 19 metres in 10 seconds, which gives us a speed 19 divided by 10, 1.9 metres per second. And so you can see that we can very easily work out the speed when we were going in a straight line. But what about when the journey is not a straight line? Well, we can reset the trundle wheel, reset the stopwatch, and I think I'll probably go from this square here. My journey this time is going to be a little bit more indirect. So let's go again. There we go, it is 19 metres in 10 seconds. What you might notice is I've not gone nearly as far away. Because my journey is no longer a straight line, it's actually around this tree, but even though I was going at 1.9 metres a second, I've only ended up just over there. And that's not nearly as far away from the starting point as it was before. It gives rise to a different measurement. And that measurement is something called displacement. If I put a tape measure just here from my starting point and I take it over here, do I measure 10 metres or do I get a different measurement altogether? What I find is rather than the 19 metres which the trundle wheel recorded, this point is only 10 metres and 30 centimetres away from that point there. Now we call this the straight line distance from where we started to where we finished, the displacement. It's a slightly different measurement to the distance which the trundle wheel recorded as I went around here. This, the shortest distance between the place where I started and the place where I finished, is the displacement. In our first example, we moved in a straight line from one position to a second position, and it was about 19 metres between the two, and we covered it in 10 seconds, meaning that we had a speed of 1.9 metres per second. But in the second example, where I didn't go in a straight line, what I found is that my total distance using the trundle wheel was still 19 metres, and I had done it again in about 10 seconds, meaning even though I had gone a curvy, twisty, turny route, I was still going at the same speed. But there is this other measurement that I made, and that was the change in position from my starting position to my final position. And if you remember, whereas the distance went all the way around the tree and back again, my displacement was the change in the position between my final position and my starting position in a straight line. And what we found was that that displacement was much shorter than the distance. And so, whereas this distance was about 19 metres, this displacement was about 10 metres. It was shorter. We could work out the speed by taking the distance and dividing it by the time. And if you remember, the distance was 19 metres and the time was 10 seconds. It means we were moving at 1.9 metres per second. But what can we do with this quantity, the displacement? Well, displacement features in a formula all of its own. If I look at the rate at which my displacement occurred, or the rate of change of displacement, then what I would get is a formula that looks almost the same, but using this change in position rather than that one. And it doesn't give me speed. It gives me a new quantity that you may have heard of before. This new quantity is velocity. If I travel in a straight line from here to there, then my distance is going to be the same as my displacement. And this means my speed will be the same as my velocity. And for that reason, you may see the two words, the two quantities, used interchangeably. Because in very simple examples, they are equal to the same thing. But velocity is more complex. Because imagine this, if I had gone on a long drive and returned back to the beginning, my speed could have been 1.9 meters a second, but my velocity would be 0. Because if I return to the place where I started, I haven't physically moved, and so that distance between my starting point and my final point that we know as the displacement would be 0, and 0 divided by anything is 0. So in situations where we are moving in a straight line, speed and velocity are the same. But in situations where I go on a path all around the houses, then velocity will become different to the value of speed. Now we're measuring speed and velocity here with a stopwatch and a ruler. There are some other ways that here in the laboratory we can measure this quantity, and we'll go through some of those now. So here is a device that will measure the speed of this car automatically. And what it is a light gate with a timer. And so what I can do here, I'm going to click on this screen and hopefully you can see. I'm going to click timing and it's going to try to detect, and it's giving me options here: time, distance, speed, velocity. I'm going to go speed and velocity at this light gate just here. Click next, and it's asking me about interrupt cards. And now this is what is on this thing here. In this example, it's a single interrupt card. And it wants to know how wide in millimeters the interrupt card is. So I'm going to measure it, and I think it is 7 centimeters. So that's 70 millimeters. So we'll just change that. 70 millimeters next, and then we're ready to go. Click finish and we'll click play to make it live. And what I'll try to do is just prop it up so that you can see. Now what I have here is a small car, and it's got this card on it which is called an interrupt card. I'm going to set this going. It's going to move through the light gate. Now, although you can't see it with your eyes, there is an invisible laser beam going from one side of the light gate to the other. As this car moves through the light gate, it starts the timer operating here. And then when the card exits the light gate and the light sensor can detect the laser crossing once more, then it sends a signal to the timer to stop counting. With a record of how wide this card is, and it has been recording how long, the time interval it took for the card to move through the light gate, it then does the calculation that we've just been doing. It takes the distance and it divides it by the time. Let's give it a go. As you can see, there we have it, 0.12. So earlier we measured the speed of the car, and we found it to be about 12 centimeters every second, or 0.12 meters per second. Here, even though it's somehow just randomly vanished, it was reading the same speed, about 12 centimeters per second. So if asked about the apparatus that could be used to measure the speed of something, a light gate and a timer can do this for you. Now there is one other piece of apparatus which could easily measure speed, and we'll talk about that now. Now this is quite old-fashioned, but this is integral to the subject of physics. This is a ticker tape timer. Now, a long time ago, so long ago that now nobody remembers, computers used to record their information on this ticker tape. It's just a massive roll of paper cut very thinly, and it appears like this, and used to be dragged through computer printers that put dots on it and all sorts. Now we have a device here that's going to put dots on this piece of paper. And you might think, what's this got to do with speed? But you need to just wait, hang on. Here is a little arm that's reaching over with a little metal needle in it. Underneath, there is an electromagnet. Every time electricity passes into and electrifies the electromagnet, it attracts the little needle down. And that would just touch the paper and go up normally, but we've placed some carbon paper, which is an ancient technology with which people used to make manual photocopies. Anyway, what happens is it presses the carbon paper and that draws a dot on the paper. The electricity we're running into here is going to tap 50 times a second. It's 50 hertz mains electricity. 50 times a second, which means the time interval between each time it taps is 0.02 seconds. It buzzes when you turn it on like this. It's drawing again and again and again that dot. But watch, the magic happens when we turn on the car. Watch this. It's dragging the paper through and dots are being drawn as we speak. Now check this out. Is this not a beautiful thing? Check it out. Can you see on this paper, and it's hard to focus, so we're going to try to get it. Can you see the dots? How beautiful. Now what we're going to try to do here is identify how many centimetres 10 dots take. So let's go here and try and get it on the scale. So here we go then. Can we see? We'll line up a dot at 40 there, and we'll see that 10 dots occur 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots, and that corresponds to about 2.5 centimetres. Okay, 2.5 centimetres is 10 dots. So now look what we're going to do. 2.5 centimetres is 10 dots. So how many metres? 0.025 metres is 10 dots. So divide by 10 means that they are basically 2.5 millimetres apart. But hopefully what you can see on my calculator there. Right, that's the distance between the dots. And we know the time interval is 0.02 seconds between the dots. And look at that, we get 12 centimetres per second, which was the same as when we measured it with a stopwatch and a ruler, the same as we measured it with a light gate. Here, using technology from the 1950s, we've been able to see the speed of the car. Now, the thing that makes velocity such a special quantity is that velocity is dependent on the direction you're going. That might take a little bit of unpacking, so let me show you this. Here I have a ruler, and this ruler is going to measure the displacement of my cart as it moves past it. Now I've defined this point as 0 and that point as 1 metre over there. As I turn the car on, it's displacing, it's going from here to there. And what you can see is that it's passed, I don't know, about 60 centimetres in a given amount of time. So it has increased in its displacement from its starting point to its finish point. The displacement was in a positive direction. It's gone from a smaller number to a higher number. Therefore, when I divide that by the time taken, I'm going to define that this motion was positive. It was in the direction that I, to start with, said was a positive direction. It means that my velocity this way is positive. It could be positive 12 centimetres per second. But having defined it as this way, how could I then define the motion of something going the other way? Well, if I've already described this way as the positive direction, and turning the car round and making it go back, well, what has happened? It's going the opposite way to the way it was going before. It has made a displacement, yes, and it's probably about the same, but it's in the opposite direction, the direction that we defined as negative to start with. That means that this has a velocity, in this case, that is also negative, because we defined this direction as negative. Negative 12 centimetres per second. So you can have positive velocities and negative velocities. It all depends on the direction that you define as being positive. Now, in physics experiments, you normally define that going to the right is positive, going to the left is negative, and if we go this way, going upwards is positive, and coming back down as negative. So here I have two cars. The car on the right, we're going to set going, and off it goes at constant speed. Isn't that amazing? Whereas the car on the left will not go at constant speed. The car on the left will have a speed that increases. So why do these behave so differently? Well, this car here, batteries drive a little motor which will make its wheels turn at a constant rate, meaning it covers the same amount of distance every single second. It moves at a constant velocity. Whereas this does something different. It takes whatever speed it's going at and the fan pushes it just a little bit more. And so whatever speed it is at, the fan is always pushing, and so what you eventually get is that the speed increases as a result of that force applying. And that force continues and continues and continues, and so it gets faster and faster and faster. The velocity increases ever up and up and up. And so this is displaying different kind of motion behaviour to this moving at constant velocity, this moving at ever increasing velocity. And we call that changing velocity an acceleration. Acceleration is something that we can measure here in the lab. And let me show you a setup that allows you to measure acceleration of an object with simple apparatus. So first things first, we're going to use the light gate and the timer. Now, we've set this up slightly differently. I've put the ramp on an incline here because I want the thing to accelerate as it goes, and I'm going to use gravity to create that acceleration for us. So on my data logger, I'm going to click the timing option, and it's going to ask me something, and I want to measure acceleration. And this is where it gets different. I'm going to measure it at the one light gate at A, and the only way I can measure acceleration is to do something like this. This car has got a double interrupt card on it. It's got two black sections on this card of known thickness, that as it goes through, it'll measure the velocity of the first one going through, all the while it's timing, and then it'll measure the velocity of the second one going through, and it will look to see how much that velocity has changed in that time interval. So this is the double interrupt card. it wants to know some details about it, so it can work out the velocity. It says 40 millimeters each time, which is that distance. I think that's correct. So let's finish, and we'll press play, and we'll take a look at what this does. So we'll just prop that up there, so that hopefully if it stands up, it'll somehow stand up. It will stand up. Okay, it totally does not want to stand up. Ah, there we go. And what I'm going to do, what I'm going to do is send the car down the slope, and hopefully we will measure the acceleration. Okay, I'm just going to, hopefully this is nice and aligned, and nothing goes wrong. What can go wrong? Okay, so it totally missed the light gate. We can fix that though. Let's try that again. And let's just have a little look at what went wrong. Let's see if we can get it to go through one more time. So I need that piece of card to go away. Okay, here we go. Here we go. Ha ha! Okay, so it went through, and it has measured an acceleration of 1.75 meters per second per second. But what does it mean? So our car started stationary, and its velocity increased until it was going really fast. It was accelerating. So let's talk about that as a quantity. Acceleration. What we need to know is how much the velocity has changed and the time interval in which that change has occurred to work out how rapidly the velocity is changing. If it's changing really rapidly, then it's a high acceleration. So we need to know what the difference in velocity is to start with. So how we would do that is we would need to measure the velocity twice. And we need to know the difference between them. And we need to divide it by the time interval between those two measurements. If we were to write this as a symbol equation, we would write it as lowercase a is v minus u over t. The symbol that we use for velocity is v. But if there are two velocities, then we'll probably use u and v. U representing initial velocity and v representing final velocity. And how do you remember the difference? U comes before v in the alphabet, so u is the initial one and v is the final one. You want to know the difference. And you can simply do that by just subtracting one from the other and dividing it by time, the time interval over which this change has occurred. So this is the formula for acceleration. What would be the units to this? Well, if you consider that velocity is measured in meters per second, and we're looking at the difference between one and another, then that's not going to change the unit, because if you think, 6 cows minus 4 cows is 2 cows. The unit doesn't change when you do adding or subtracting of quantities, but it does change if you divide by something else. Like if I wanted to know how many cows were going by every second, it would be cows per second, wouldn't it? But if I'm dividing here meters per second and dividing that all by seconds, it creates a unit for acceleration, which is sometimes called meters per second, or, using a little bit of fancy mathematics, meters per second squared. That is the unit. When the acceleration is high, then the rate of change of velocity is high. When the acceleration is low, the rate of change of velocity is also small. If I define this way as positive, then I could accelerate in a positive direction. Or I could accelerate in a negative direction. These are both accelerations. One positive, one negative. But I want you to imagine this. If I push my car in a positive direction so that it's already travelling this way, what I've done now is I'm going to turn the fan on so it's pushing with this propeller in the opposite direction to its velocity. So I'm going to push it this way, but the fan's going to be pushing it that way. What's going to happen? I'm going to push it in the opposite direction to the direction that the fan is trying to change its motion. I turn it on, and I push it this way. What happened? Well, to start with, it had an initial velocity that started to decrease until eventually it reached 0. When I have this starting condition, that I have a velocity in a particular direction, but that the acceleration acts in the opposite direction to the direction it is already moving, then we give that a special name. We call that a deceleration, because what it does is it slowly decreases the velocity in the given direction with time. Now, what you need to keep really clear is the difference between a negative acceleration, which is just an acceleration that is going in the opposite direction, to a deceleration, which is an acceleration that's going in the opposite direction to an established forward movement, to slow down the object. It is only ever a deceleration when it is acting against the motion of the object. Now, when it comes to motion, we can draw this on a graph, and nothing gets a physicist more excited than a graph. So what I have here is I've got this motion detector. It actually sends out a ultrasound pulse of waves that bounces off this card, and it listens for the return. And knowing the speed of sound and multiplying that by the time it takes gives the distance there and back again. Dividing by 2 tells you exactly how far away that is. And I want it to plot how far away it is every single second. And it's going to draw it on here. So come get a closer look. Right, so I'm ready to draw a graph here. When I press play and I set this going at the same time, it's going to record every few milliseconds just how far away my car is. I press play. And I start it off. Off she goes. Check it out, folks. There she goes. And back to the graph. Look at that. It was, with the occasional little blip here and there, a straight line. This is a distance time graph. And whilst this car was moving at constant velocity, it was just a straight line with a constant gradient going up. But what do other motions look like? What, for example, does an acceleration look like? Well, so this here is a dead bat it's a historical sample, so it's probably 100 years old or something like that. But I'm showing it you because bats actually have something called echolocation. They send out this cheeping ultrasound pulse that hits objects and then bounces back. And with that, they are able to identify like moths flying in front of them, even in the dark. And we use that same technology in this, a motion sensor. And you probably can't hear it, it is chipping every now and again, and I can just hear it. An ultrasound pulse is leaving this, and it's hitting this card that I put on the front of the fan car. Now what I want this to show me is what a distance time graph looks like for an object that is accelerating. So we're going to set this going and I'll show you the results. So first things first, we press play and then we set the fan car going. See, brilliant. Now I'm going to take you in closer to show that there's no manipulation going on here. This is the graph that was drawn. And can you see that it is no longer a straight line, but it is curved? This is the distance time graph for something that is accelerating. So if we were interested in displaying the velocity of the object at various different times in this journey, we would have to plot a velocity time diagram. Now, Mr. Ferguson has set up this demonstration for us. What it is, it's the car that should be driving at constant speed. And what we've done is we put a blue tack spot on it so that this camera here can track the motion of this car. Ready?
So, just going to commence filming. Okay. And stop.
So now we'll go process that and we'll see, hopefully, a velocity time diagram for a car moving at constant speed. So we have taken that footage and we've uploaded it onto this tracker software. Mr. Ferguson is going to show us the graphs.
Right, you can see here that you've got the distance here against time and you've got a nice straight line. If I now click on the X, it's called X here, but it's actually on the Y axis, and now go down to velocity in there, we can see you've got a straight line here. And we can expand these lines by just clicking on the triangles here and getting it to go across, and I want to increase that there. So you can see that it's, you can see the variations, very small variations, where it's trying to take the values from the screen position.
So with a distance time graph, a constant velocity was an uphill slope with constant gradient. But on a velocity time graph, that same constant velocity is just a flat line. And this is because on the y-axis you have velocity and it is constant, it is not changing, and so it is flat. Now we want to change this, and we want to see what an acceleration might look like on this software. So now we want to see what an acceleration looks like on a velocity time diagram. So what we've done is we've raised one half of this ramp up to make something that in physics we call an inclined plane. We have the car and we have the little tracking wall of blue tack on it. When you're ready, Mr. Ferguson, you capture the motion. So a velocity time diagram of an acceleration, what did we get?
Well, this is the displacement time. You can see the curve on it. So if I change the axes now to show the velocity time direction, you can see it's very proximate, very close to being a perfect straight line. You've got small variations in the frames, but that's due to the camera interpreting the position.
So with a distance time graph, the acceleration was a curve whose gradient was always changing. But on the velocity time graph, it was a straight line going up as the velocity increased with time. So let's pull that together. I'm going to draw a distance time graph on the left and a velocity time graph on the right. Now for both of these, time goes on this axis, and we're going to measure it in seconds, though you can see graphs where they have chosen to measure it in hours or years, but for the laboratory it's more likely in seconds. Now on this axis, the y-axis, we want to record the position of the car. Now you may see some confused thinking about this. In some places they will put distance up here, and it's even possible for you to see that they have put displacement up here. Now, remembering that both distance and displacement in their own ways are just the difference in position between here and there, then actually it's not accurate to call this axis either distance or displacement, because really it's just measuring the position of the object at a given time. So perhaps the best ones are the ones that just have x, where x represents just how far you're away from some certain point. But for the sake of GCSE, you're most likely to see distance written on this axis, so I'm going to put that on as well. So distance here in meters. Now, of course, I'm going to put some numbers in here, but these are just to show 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Now, there are different things that I can draw on here, different types of motions. If I remained stationary, so I was 1 metre away, and after 1 second I was still 1 metre away, then you can see a flat line is how I would depict that. I could move further away, so I'm going to try to get to that point there. So what's happening here is over the course of the next 2 seconds, I moved from my position of 1 metre away to 3 metres away. And you can see that that is 2 metres in 2 seconds, which would be 1 metre per second. I could come back again. I could return, so I'm going to return to this point here. I could return like this. And a line whose gradient is negative coming down simply means I'm returning back to where I started from. I could, and what I'm going to do is I'm going to go up from 7 all the way up to 6 up here. If I can, I want to draw a really sharp line like this. Now notice that the gradient of this line is greater than the gradient of that line. This tells us something. What it tells us, and we get another colour pen, is about the motion of the object. And this is why a distance time graph is so useful. What I can do, first of all for this one here, I'm going to draw a gradient triangle onto this shape here, because I'm interested in this. And I know that this point is 3 and this point is 1, so the difference is 2. This is 3 and that is 1, so the difference is 2. Now here, the gradient is just this vertical number, the difference in the distance, divided by this difference in the time. And distance divided by time is going to be 2 divided by 2, which equals 1 metre per second, which means that the gradient is equal to the speed. Now remember what we said, if the object is moving in a straight line, the speed and the velocity are going to be the same. It's quite possible that even on a distance time graph, so long as it is going in a straight line, that the velocity would also equal the same value as the speed, because it's going in a straight line. Now this one here is a steeper line, so let's have a look at this one. So we're going to draw a line straight down there. And it's always good to draw the largest triangle that you physically can with your data. So how high is it? It goes from 1 to 6, which means it's 5 high and 2 wide. So that's the first speed. This is the second speed, which is again the gradient, but of this other line, is equal to the distance divided by the time, which is equal to 5 divided by 2. So here, it's 2.5 meters per second. You can see that a steeper line actually represents a faster motion. So a higher velocity or a higher speed when the line is steeper. On this section here, it's the same gradient as that section there, but it's downwards. And so we would actually represent the motion here as -1 meters per second, because we are coming back towards the origin. Now, if we were talking strictly about speed, the speed doesn't become negative, but in this instance, we're kind of representing it as a velocity, which you can see is a bit strange considering we have distance on that axis, but never mind. Now, there's one more thing that I want to draw on this diagram. If we've said that the gradient represents the speed, what happens if the gradient changes? So imagine that none of this is here, but if I had an object that was 5 meters away and it started to do this, well, there is a curve. I could draw the gradient at any point and find that the gradient is getting more and more and more. It means it is speeding up. This is an acceleration. So the number one rule about distance time graphs is that the gradient represents the velocity or speed of that object. Now let us consider the velocity time graph. We're going to put velocity on this axis in meters per second. And again, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Oh, no, I went higher. Now here, getting my other pen, the rules change. This here, staying stationary for 1 second, would have my velocity like this at 0 for 1 second. So then it runs at 1 meter per second for 2 seconds before becoming -1 meter per second. I can actually go down here for the -1 for another 2 seconds. And then for the final 2 seconds, it goes up to 2.5. So you can see, when I've got these velocities instantaneously changing, then what I have is this blocky pattern on this. Now let us consider this. If it was 2 meters every single second and it was starting at 0 meters per second, so it's down here, then in the first second it is increased by 2 meters a second. In the second second it's increased by 2, and then 2, and on. And so what you can see is that that acceleration that we had depicted there, well, this is supposed to be a straight line, would look like that. And on a velocity time graph, a curve like this represents an acceleration. And you notice that that is a curve, and this is just a line that is going up. The velocity is increasing as time goes on. Now, I could work out the value of that acceleration by taking the gradient. The gradient of this line will tell me what the acceleration is. And here, there are no gradients. But there's something else we can work out from this graph. If we take, for example, this here, then if I was to work out the area under the graph, and you can see there's this area here, which is 1 times 2, and there's this area here, but this is negative, so this is -1 times 2, and then there's this area here, which is 2.5 times 2. What we can see when we add them all together, 1 times 2, which is 2, plus -1 times 2, which is -2, they cancel out, and we end up with 5 meters. The area under the graph represents how far you've gone on a velocity time graph. So the area equals your distance travelled. So the 3 rules are, on a distance time graph, the gradient gives you the speed or velocity. The second rule, on a velocity time graph, a slope like this, the gradient gives you the acceleration, different thing. And then the final rule is on a velocity time graph, the area under the graph between the line and the x-axis gives you how far you have travelled.